Okay, a little practice working backwards here. Each of these is the graph of a derivative, and from the derivative we must figure out what the original function looked like. Now, we can do this just from the diagrams, and there are also some tricks we can use to make this go easier. For this first one, if the derivative is a straight line, that means the derivative is first degree. It's something x to the 1 plus maybe some number. In fact, this looks like negative x plus 1 pretty much. What does that tell you about the original function? You know from the power rule that every time you do a derivative, the degree of the thing you're differentiating drops by 1 if it's polynomial. So if the derivative contains x to the 1, then the original function must contain x to the 2. And so just from the fact that this is a straight line, we know our original function is probably a parabola of some sort. Now, let's see what else we can figure out about it. Looking at how this derivative behaves, here it's positive and it's kind of big. This derivative is 3 or something like that, which means over here our function is increasing fast. The higher the derivative gets, the faster the function's increasing. So this is increasing rapidly. Then it drops and drops and drops and drops. Over here, the derivative is positive, but not all that big anymore. And so we could say our original function is increasing, but slowly. What does this mean? Right there. At that point, the derivative is 0, which means the slope of the curve is 0, which means the curve is flat. Over here, where the derivative is negative and small, we'd say the function is decreasing slowly. And as the derivative gets bigger, our function, it's still negative, so the function's still decreasing, but it's now decreasing faster. So if you try to draw a curve that increases fast, then increases slower, then it's flat, then it decreases slowly, and then it decreases faster, sure enough, you end up drawing a parabola. So this, or I'll scale it up a little bit, this is probably a fair rendition of the original f of x. Now the trouble is, if this function had a y-intercept, if it had a plus c on the tail end of it, I have no idea what that is, and there's no way to get it back because that number gets lost when you differentiate it. So this curve is possible, so is this one, and this one, and this one, and this one. We have no idea what our y position is, but at least as far as the slope, we can say this curve should look like an upside down u, or a parabola opening down. For the second one, we can pretty much use the same approach. This derivative, f prime of x, looks quite a bit like a parabola. It's something of second degree. What does that tell us about the original function? Probably third degree. I shouldn't put equals, I'll say approximately or similar to x to the third. So our original should be a cubic or have cubic looking behavior. And in more detail, what does that mean? If this is our derivative, just like before, we can say when it's big and positive, this means our function is increasing fast. Over here would also be increasing fast. Here, where the derivative is positive but not so big, we get increasing slow. Over here is also increasing slow. There are two spots here where the derivative is 0, meaning there are two spots where our function should be flat. And down here, the derivative is negative, which means our function should be decreasing. I'm going to say slow, the numbers aren't all that big. It decreases slowly, then quickly, then slowly again, as the derivative goes small, bigger, smaller. So, if we read our way across this from left to right and try to draw something that answers that description, I'll just start here in the middle. Increasing fast, okay. Then we get increasing slow, so slow it down. flat, decreasing, slowly, then a little faster, then a little slower, then flat. I did that a little too soon, but it flattens out. Then it increases slow, and then it increases fast. All this is behavior you'd expect to see from a cubic, and it's supported by what we're told about the derivative. Again, we have the problem where we don't know where this is vertically or what its y-intercept is, but at least we have the general shape. That's what you get from the derivative.